This is lesson 1.1, using the language of algebra. Our learning objectives are to find factors, prime factorizations, and least common multiples, use variables and algebraic symbols, simplify expressions using the order of operations PEMDAS, evaluate an expression, identify and combine like terms, and translate a phrase to an algebraic expression. This is our first lesson of this course, so I will show you how things will happen. We will address each learning objective one at a time. There will be definitions in the gray boxes, and I will provide examples on the left-hand side. You can pause the video and try the problems on the right-hand side, the try it section. So let's move into our first learning objective, finding factors, prime factorizations, and least common multiples. We first run into definitions. A number is a multiple of n if it is the product of a positive integer and n. If a number m is a multiple of n, then m is divisible by n. These definitions of multiple and divisible take on meaning as we look at a multiplication chart. In this course, you'll want to be comfortable multiplying numbers from 1 through 15 and breaking them back into pieces. So here our multiplication table, we'll choose a number like 48. Now 48 is a multiple of 4 and 12 according to this table because 4 times 12 is 48. And 48 is divisible by 4 because the result is 12, and it's divisible by 12 because the result is 4. So the meaning of these definitions, multiple and divisible, take on life just from visualizing a multiplication chart. You could do this with any of the numbers in this chart. For example, we could choose the number 27, and we know that 27 is 3 times 9. So 27 is a multiple of 3, it's also a multiple of 9, and 27 is divisible by 3, and it's divisible by 9. Another important feature of this multiplication table is the diagonal here in green. These are called the perfect square numbers. We will use them often in this course, and you will want to be comfortable with them. They are called perfect squares. You'll recall that multiplying the same number by itself is called squaring something, or raising it to the second power. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, etc. Now, let's address some of the larger perfect square values, like 9 squared is 81. 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, and 15 squared is 225. If you memorize and get comfortable with these values, you will find them very useful as we move forward in this course. So how do we know if a number is divisible by a certain smaller integer? Well, we can run divisibility tests. Now, a number is divisible by 2 if the last digit is even, 0, 2, 4, 6, or 8. It's divisible by 3 if the sum of the digits is divisible by 3. It's divisible by 5 if the last digit is a 5 or a 0. It's divisible by 6 if it is divisible by both 2 and 3, and it's divisible by 10 if it ends with a 0. Here in example 1.1, I will take a large number, 5,625, and I'm going to check. I'm going to run a divisibility test. Is it divisible by 2? Well, I'll say no, because its last digit is 5, which is not even. Is it divisible by 3? Well, I will add the digits together, 5 plus 6 plus 2 plus 5, and that gives me 18. Now 18 is divisible by 3, so I will answer yes. Is it divisible by 5? Yes, because the last digit is a 5. Is it divisible by 6? Well, is it divisible by 2 and 3? Well, it's not divisible by 2, even though it's divisible by 3, so I will have to say no. And is it divisible by 10? No, it doesn't end with a 0. You can try the example problem on the right. Let's talk about factors. If m equals a times b, and both a and b are integers, then a and b are factors of m. It's like going back to the multiplication chart and looking at the numbers that are the pieces of the bigger number. Like if I saw 55, I would recognize the factors of 55 as 11 and 5. Sometimes numbers have more than one set of factors, and we can address that. Now, prime number. A prime number is an integer greater than 1 whose only factors are 1 and itself. A composite number is an integer greater than 1 that is not prime. Let me show you a factor chart to help you with prime numbers versus composite numbers. So a prime number is one that has only one set of factors, 1 and itself. Now, the number 1 is neither prime nor composite. So it's not prime or composite. So the prime numbers begin at 2. And so here in red, I will circle prime numbers. See, we see 2, 3, 5, 7, 11, 13, 17. These are prime numbers because they only have one set of factors. Composite numbers are composed of more than one set of factors. So 4 is a composite number, 6 and 8 and 9 and 10. These are composite numbers. Now, how can you find prime numbers for yourself? I'm going to show you a quick method to find all the prime numbers up to 50 for yourself. So here are all of the integers from 1 to 50. We know that 1 is neither prime nor composite. So prime numbers begin at the number 2. And if I have a prime number, all of the numbers that are multiples of that number can't be prime. They must be composite. So all of the multiples of 2, they are not primes, so I'll cross them out. Now, once I cross all of the even numbers out, which are multiples of 2, I move on to the number 3. And 3 is a prime number. Its only factors are 1 and itself. And I can now cross out all of the multiples of 3, like 6 and 9 and 12 and 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, 48. Those are all the multiples of 3. I move on in this list and I get to a 5. 5 is the next available number. And 5 is prime. It only has factors of 1 in itself. So all of the multiples of 5 can be crossed out, like 10, 15, 20, 25, 30, 35, 40, 45, and 50. I now move on to the next available number, which is 7. And I cross out all of the multiples of 7, like 14, 21, 28, 35, 42, and 49. Now, what's interesting about what we've just done is all of the remaining numbers that are not crossed out, they are prime numbers. So we have 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and 47. These are all prime numbers. I hope this has been helpful for you deciding what prime numbers there are up to 50. All of the other numbers are composite because they're composed of more factors than just one in themselves. Now, a prime factorization is the product of prime numbers that equals the number. all composite numbers are composed of prime numbers multiplied together. We can break a composite number down into all of its primes multiplied together. I'll show you an example with the number 48. So 48 can be broken down into pieces. 2 times 24. And then 24 can be broken down further into 2 times 12. And 12 can be broken down into 2 times 6. And 6 can be broken down into 2 times 3. So you see, we are breaking numbers down into pieces using a factor tree. And these numbers here are the primes that multiply to make 48. So 48 is equal to 2 times 2 times 2 times 2 times 3. This is called the prime factorization. You can do this with every composite number that exists. All right? Another way to write this is 2 to the 4th power times 3. Because there are 4 2's multiplied together, I can call that 2 to the 4th. Let's now talk about least common multiples. A least common multiple is the smallest number that is a multiple of both numbers. In example 1.3, we need to find the LCM, or least common multiple, of 12 and 18. So what I would do is create a list of the multiples of 12. 12 times 1 is 12. 12 times 2 is 24. 12 times 3 is 36. 12 times 4 is 48, etc. Now I will also create a list of the multiples of 18. So 18 times 1 is 18. 18 times 2 is 36. 18 times 3 is 54. 18 times 4 is 72, etc. Now, what you'll observe is that there is a number that appears first on both lists. The number that appears first on both lists is the least common multiple. So I'll respond that the LCM is 36. Now, there may be other numbers that repeat again, like this number 72. It's a common multiple, but it's not the least common multiple. Let's move on. In this course, we will learn to use variables and algebraic symbols. A variable is a letter that represents a number whose value may change. And a constant is a number whose value always stays the same. So let's talk about a variable. A variable could be any letter. It could be any symbol. So often we use the letter X to represent a variable, but we could use the letter T if we're discussing things in terms of time. We could use any letter that we want to. We could even use Greek letters like theta or alpha. Okay, so variables are just letters or symbols that represent a number. And that's what makes algebra algebra. So before you used any letters in math, you were using all numbers, and that was called arithmetic. Now that you have incorporated variables and input letters, we now have algebra. Now a constant is just a number, like 3 or 5. It doesn't change. It is a value that stays the same. All right, so we've got variables and constants. In this course, we will have a lot of operation symbols that we use and inequality symbols. So let's just review those quickly. Now, the basic 4 operations of math is addition, subtraction, multiplication, and division. So the result of addition is called the sum. The result of subtraction is called the difference. The result of multiplication is called the product, and the result of division is called a quotient. You will see these words often in this course, and whenever you see these words, you'll think of the appropriate operation. We also will be using inequality symbols in this course. So if we take an equal sign and put a slash through it, that means is not equal to. So that's the not equal to symbol. We also have a less than symbol, like A is less than B, less than or equal to symbol, A is less than or equal to B. We have a greater than symbol, A is greater than B in this case, and a greater than or equal to symbol, A is greater than or equal to B. So make sure you're comfortable with these inequality symbols. We will be using them throughout this course. Now, an equality symbol is just the equal sign, right? So A is equal to B. Also, we have grouping symbols like parentheses. If we've already used parentheses, then we may use brackets. And if we've already used parentheses and brackets, we may use braces. All right, so here are some more definitions. An expression is a number, a variable, or a combinations of numbers and variables using operation symbols. So I will give you an example of an expression, like 3x plus 5. This is an expression. Another expression might be 2x minus 4. Now, these two expressions are simply a mathematical statement. They are simply mathematical statements. But if I put an equal sign between these expressions, this whole thing becomes an equation. An equation is two expressions connected by an equal sign. We're also going to be using exponents a lot in this course. So exponential notation is a to the n means multiply a by itself n times. So if I had 2 to the 5th power, okay, this exponential notation would mean I take the base 2 and I multiply it by itself 5 times. And so 2 gets multiplied by itself 5 times, and the result is 32. Great. Now, we will also need to be able to simplify expressions in this course. So we'll take an expression and we'll simplify it as much as possible using the order of operations, PEMDAS. PEMDAS stands for parentheses, exponents, multiplication and division, and addition and subtraction. So when we see an expression with parentheses, we address the parentheses first, then we move on to exponents, then we'll address multiplication and division from left to right. And finally, we'll address addition and subtraction as we see them from left to right. Just a note, multiplication and division have the same importance, and so do addition and subtraction. They have the same importance. So we're just addressing them as we see them from left to right. Here's example 1.4. It says to simplify the expression 18 divided by 6 plus 4 times 5 minus 2. So as I look into this, I see parentheses. So let's simplify the parentheses first. 5 minus 2 is 3. So I have 4 times 3 right there. Okay, and now let's address the multiplication and division that we see from left to right. So 18 divided by 6, well, that's 3, plus 4 times 3, which is 12. I finally address the addition that I see. 3 plus 12 is 15. Let's try that again. Example 1.5. We'll simplify the expression 5 plus 2 cubed plus 3 times 6 minus 3 times 4 minus 2. You'll see I have parentheses, and since we've already used parentheses, the larger grouping symbol is brackets. Let's go ahead and dive in. I see 4 minus 2, which I'll turn into 2. So I have a 3 times 2, all this stuff in brackets, right? So we've rewritten stuff, cleaned up a little bit. Let's clean it up even further. So I see 5 plus, I can address the exponent of 3. So 2 cubed is 2 times 2 times 2, which is 8, plus 3 times, well, 6 minus, Well, this becomes 6 minus 6, which is 0. So I get 5 plus 8 plus 3 times 0. And so 3 times 0 cancels, and 5 plus 8 is 13, and this is my final result. I have simplified fully the expression. All right, moving forward, our next objective is to evaluate an expression. Now, to evaluate an expression means to find the value when the variable is replaced by a given number. You will be expected to evaluate expressions and functions often in this course. So I'll just tell you that when you see the word evaluate, it means to plug in. We're plugging in a number for a variable. Example 1.6 says evaluate each expression when x equals 4. So part A, I see x squared. I will replace x with 4, so I get 4 squared. Right? And so 4 squared is 4 times 4, which is 16. Okay, now part B, 3 to the x becomes 3 to the fourth. And 3 to the fourth is 3 multiplied by itself 4 times, which is 81. And let's evaluate 2x squared plus 3x plus 8 when x is 4. So I rewrite this all as 2 times 4 squared plus 3 times 4 plus 8. And remember to follow the order of operations. We apply exponents before multiplication. So 4 squared is 16, and 16 times 2 is 32. I add that with 12 and add that with 8. And my final result is 52. All right, so we have practiced evaluating an expression, meaning plug in a certain number for the variable. Our next learning objective, identify and combine like terms. Now, a term is a constant or the product of a constant and one or more variables. I'll show you a variety of terms, like if I had 3x squared and I have 5x and 7. These are 3 different terms. Terms are separated by addition and subtraction. So I've got addition here or subtraction here, which means that I've got this term, and this term. Terms are separated by addition and subtraction. Now, a coefficient is the constant that multiplies the variable in a term. So these are examples of coefficients, right? They are the number that is multiplying the variable, coefficient. And like terms. Like terms are terms that are constants or have the same variables raised to the same powers. So like terms have to have the same variable with the same power. So in our case, 3x squared is not a like term with 5x because the variable x has different powers. And then you'll see the constant 7 at the end. That is not a like term. It does not have the variable x, and it does not have the same power of x. Let's practice combining like terms in example 1.7. It says to simplify 2x squared plus 3x plus 7 plus x squared plus 4x plus 5. I see 6 terms. Let's look to see if any of the terms are like terms with the same variable and the same power. So looking at the first term, 2x squared, I see another term that has the same variable and power, 1x squared. I can combine like terms, so I turn that into 3x squared. There are 2x squareds, and I add 1x squared, that's 3x squareds. Moving on, I see a 3x and a 4x. Those are like terms, same variable with the same power. So 3x plus 4x is 7x. And lastly, I see constants, 7 and positive 5. So I can add 7 plus 5 to make 12. In this case, the operation of addition happened between all of the terms. There were no subtractions. So here's my final result. Lastly, our goal now is to translate an English phrase into an algebraic expression. So we need to be able to turn sentences in English into math notation. Example 1.8, translate. Now we're going to see the words sum, difference, product, and quotient, which you'll remember apply to addition, subtraction, multiplication, and division. So looking at this, I see the word difference, the difference of 14x and 9. So I'll take 14x and I will subtract 9 to find their difference. The quotient of 10x squared and 3. When I see the word quotient, my brain tells me division. So I'll take 10x squared and I will divide it by 3. When I see the word more than, I think of adding. So I'm going to take y and add 12 more. When I see the phrase less than, I think subtraction. So 7 less than 49x squared, I will take 49x squared and I will subtract 7 from it. Be careful. With subtraction, it's important which thing goes first and which thing goes second. So 7 less than 49x squared is 49x squared minus 7, not the other way around. Do not write 7 minus 49x squared. Example 1.9, translate. Part A, 8 times the sum of x and y. So if we take the sum of x and y, we would want to then multiply it by 8. We would have 8 times the sum of x and y. For part B, it's slightly different. The sum of 8 times x and y. So I want to take 8 times x and sum it with y. These two parts are slightly different from each other and would result in two different things. So be careful as you read English and convert it into math expressions. Example 1.10, the length of a rectangle is 14 less than the width. Let W represent the width of the rectangle. Write an expression for the length of the rectangle. So we want to highlight certain phrases in the paragraphs that we read. Okay, so I will highlight the length of a rectangle is 14 less than the width. So if I took the width and I subtracted 14, that's what the length would equal. So this is the expression for the length. I can write length equals width minus 14. Lastly, example 1.11. June has dimes and quarters in her purse. The number of dimes is 7 less than 4 times the number of quarters. Let Q represent the number of quarters. Write an expression for the number of dimes. Looking at this paragraph, I would highlight the important pieces. And I want to create an expression for the dimes in terms of the quarters, Q. So I take the variable Q, and I know that it's 4 times the quarters minus 7. Right? So I read the phrase 7 less than 4 times the number of quarters. And that's what the dimes are. So the expression for the dimes is 4Q minus 7. We've now completed the first lesson. Any problems on the right that you want to try for yourself? That's a great practice. Also, for every lesson, there is an associated assignment. So now that you've completed lesson 1.1, You can now look at the assignment 1.1 in WebWork. Thank you.